Hey there, we're going to go over some circular motion notes. And so first, let's go ahead and describe what circular motion is. And circular motion is when an object is revolving around an external, I'm going to underline this word here, axis. So later in the year, we're going to start talking about objects that are revolving around an internal axis. And so that's what we call rotational motion. But we're not talking about that right now. We're talking about circular motion. And so it's an object revolving around some external axis. So let's kind of draw and see what that looks like. So let's say this is Earth here. Oops. And then we have some kind of satellite, and it is in circular motion around the Earth. And so we have two objects here, right? We have the Earth, and then you have your satellite. And so kind of the center of your circle would be right there in the center of the Earth, and it's in circular motion around an external axis, right? Because it's over here. It's not within itself here. So it's in circular motion. So the key thing here is we're not rotating. Okay, we'll get into that a little later. And so let's go ahead and draw ourselves another circle. Oops. And let's say that what we have here is I have a string that's attached to some kind of a ball, and I'm swinging it in a horizontal circle. So right now we're just kind of talking about horizontal circles. We'll get into vertical circles in a little while. And so this is kind of like a top view. Okay, we're kind of looking down at this ball that's being swung around in a horizontal circle. And so the first kind of idea behind objects in circular motion is that they have uniform speed. So in other words, it's the same constant speed. And let's say as we're swinging this, and let's go ahead and we'll say that we're swinging it kind of counterclockwise here. And right about here, the string snaps. And so what's going to happen to your ball that you're swinging, it's going to fly off. And when it does, it's going to fly in a straight line, like this. Same thing right here. Let's say it snaps up here at the top of the circle. It's going to fly off this way in a straight line. And if it does it right here, it's going to fly off. And right here, it's going to fly off this way. And so the reason why it would do that is we learned it last semester. That was Newton's first law. An object that's in motion will stay in motion in a straight line unless you have some kind of unbalanced force. And so these lines here are actually our velocity vectors. Okay, the velocity vectors for an object moving in circular motion is going to be a line that's tangent to your circle. Now, the next question that we'll kind of ask ourselves is this object here accelerating? And so when we look at the constant speed, right, this uniform speed, initially you might say, no, it's not because it's moving with a constant velocity. But if you look at your velocity vectors, the direction is constantly changing. So the answer to this question is yes. And the reason why is because your direction is constantly changing. So because the direction is constantly changing, this object is in circular motion is accelerating. And so if we go in and we want to draw our acceleration vectors, how it would look on this circle here is it would be pointed towards the center of the circle at all these spots. So this would be my acceleration. Here would be my acceleration. Oops, it's kind of crooked. Here is my acceleration. Acceleration. So your acceleration is always pointed towards the center of your circle. And so when an object is moving in circular motion, we actually call that a centripetal acceleration. Centripetal just means a center-seeking acceleration. And our little symbol that we use for this is A subscript CP, okay, centripetal acceleration. Now, the next thing that we can kind of talk about is since it does have an acceleration, that means there has to be some kind of unbalanced force here. And so without an unbalanced force, this object would move in a straight line. But because there's an unbalanced force, there's some kind of force that's keeping it moving in this circular motion, which is causing it to have an acceleration. And so we call that a centripetal force. And we use the FCP, centripetal force, to kind of denote a force that's causing an object to move in a circular motion. Now, be careful here. This word here, centripetal force, it's just a descriptive word. So it's not an actual force. I wouldn't say the centripetal force is equal to 5 newtons. It's just a descriptive word. So any force can be a centripetal force. So in this case here, what was the force that was causing this ball to move around in a circular motion? It was the string or the tension in the string. And so in this case, I would say my tension is centripetal. And this other one here that we drew, there was a force that was keeping this satellite in circular motion, and that force was a gravitational force. So in this case, your force of gravity would be a centripetal force. It would be centripetal. And so that's all a centripetal force means. It's a force that's kind of causing an object to move in circular motion. Now let's kind of get into some of our new equations that we have for circular motion. So the first one is velocity. And so we have velocity is equal to, remember earlier in the year we said it was displacement over time. And if we think about one time around this circle, so one full revolution around this, then your displacement would be the circumference of your circle. And remember, the circumference is equal to 2 pi r divided by, now your time is going to be the time to make one revolution, one revolution around this full circle. And we use a capital T for that. And so this capital T is also known as period. Okay, so it's a time for one full revolution around this. So the velocity is just equal to 2 pi r, the circumference of your circle. So all of this is your circumference. Divided by the period, or the time for one revolution around it. We also have an equation for acceleration, and that centripetal acceleration. So centripetal acceleration is equal to v squared divided by the radius. Now, we could kind of go through and derive this equation. It takes a lot of, either geometry or calculus. So we'll kind of skip that for now. Both of these equations here, this v equals 2 pi r over t. I'm sorry, no, this one is not on your chart. So this one, you'll have to kind of commit to memory, but it's relatively easy because it's just the circumference of the circle divided by the time for one revolution, or the period. Your centripetal acceleration, that one is on your equation chart, so that's not one that you have to commit to memory. Now, we also had mentioned that there was this centripetal force. So we do have an equation for centripetal force. And let's think back of Newton's second law. Newton's second law, we said acceleration was equal to the net force divided by the mass. And if I rearrange that for my net force, you get net force is equal to the mass of the object times the acceleration. So all we're going to do here is we're going to substitute for the acceleration our v squared over r. And so the equation that we get is that the centripetal force is equal to mv squared divided by r, and r being the radius of your circle. So we have three equations here, three new equations, one for a centripetal force. We also have one for centripetal acceleration. And then this other one, it's really the same equation we've been using. Velocity is displacement over time. It's just now my displacement is going to be the circumference of a circle divided by that period. So this one right here. So let's go ahead and work an example problem together and using some of these new equations. So this one says we have a 0.13 kilogram rubber stopper. It's attached to a 0.93 meter string. The stopper is swung in a horizontal, okay, so right now we're still talking about horizontal circles. And it makes one revolution in 1.18 seconds. And then we're asked to find the force exerted by the string on the stopper. In addition to that, we're going to find the velocity and the centripetal acceleration as well. So let's start with A, finding the velocity. Now let's go ahead and draw this out. So we have a circle. And kind of write down what we know. We know that the mass of your rubber stopper is equal to 0.13 kilograms. And we know that the radius, so your string is from the center here to here. This is my radius, which is 0.93 meters. So my radius is equal to 0.93 meters. And it says one revolution. Remember, that represents that period, that capital T. So your period is equal to 1.18 seconds. And now we're asked to solve for the velocity. Okay, so our equation that we have is v is equal to 2 pi r divided by t. And so we know the radius, we know the period. Now we can just plug in our numbers. So your velocity is equal to 2 pi times 0.93 meters divided by 1.18 seconds. And when you plug that in, you should get a velocity of 4.95 meters per second. And then part B, we're asked to solve for the centripetal acceleration. So we'll just make B right here. And so your centripetal acceleration is equal to v squared over r. We just solved for our velocity, so 4.95 meters per second. divided by the radius, which is 0.93 meters. And then this, don't forget to square this here. So when you plug that in, you should get a centripetal acceleration is equal to 26.3 meters per second squared. And then finally, for part C, we're asked to find that centripetal force. Make C right here. So the centripetal force here, which is my tension in the string, is equal to mv squared divided by the radius. So that's going to equal the mass, which is 0.13 kilograms, times the velocity, which we found earlier as 4.95 meters per second. And that's squared divided by the radius, which is 0.93 meters. And when you plug that in, you get this centripetal force, which is your tension, is equal to 3.42 newtons. Let's look at another example. This one says we have a 500 kilogram car traveling 20 meters per second. It makes a left turn, and the radius of the turn is 400 meters. And we're asked to calculate the friction force between the car and the road. So to kind of start this one, let's make a free body diagram. Now we know we have Fg down and normal force up. But as this car is turning, it's not slipping, right? It's not skidding. And so what we have here is a friction force, and that's what's keeping the car in this circular motion as it's turning. And so in this case, my friction force here is going to be centripetal. Okay, so your friction is centripetal. And we know that our new equation for a centripetal force is mv squared divided by r. And so since friction is centripetal, we can set this equal to your frictional force. And so now we just need to plug in our numbers. So you get the mass, which is 500 kilograms, times the velocity squared, so 20 meters per second. That's going to be squared, divided by the radius, which is 400 meters. And when you plug those in, you should get a frictional force is equal to 500 newtons. So there's your new equations for circular motion and kind of how to apply those. And then we'll do some more practice in class.